Okay, so before we get going on the packet, I want to show you guys this website, and you can actually get to this site by going to my website, and then what we have today, graph the derivative activity. Click on that. It takes you to this. Now it starts off with a parabola because I want to show you how this works, and then we're going to do it for the new things. So for a parabola, y equals x squared. You already know. So I'm going to just go straight to the punchline here. You already know what the derivative of x squared is. What?
2x.
2x. So when I graph the derivative here, it's going to graph the line y equals 2x. That's not news. That's old news. All right, and so what I'm going to do next is we're going to go through e to the x and natural log of x. Okay, so first, e to the x. Now remember, this is your exponential growth function. And I'm going to just start with the tangent line. So let me start over here, way to the left. Notice the derivative, aka the slope of the tangent line, is really close to what? It's close to 0. And as x gets bigger, what happens to the slope?
It increases.
It increases. And it is always positive, right?
Right.
So increasing at an increasing rate. So if I click this right there, what it will do is it will plot and then trace the derivative. Now before, saw how it traced that derivative line? Look at what's happening here. It completely traces over the original graph, which is kind of strange. This is unique to e to the x. The derivative of e to the x is e to the x. Okay, did y'all catch that? What's the derivative of e to the x?
E to the x.
E to the x. What this means is, if you take any place along this curve and you find the slope at that point, it's the same as the y value at that point. This only happens in this one case. There's no other time when this happens. Every other time you take derivative, you get something new. Okay? Here, derivative of e to the x is e to the x. Now, I have very informally proved this to you by showing you this applet that graphs derivatives and then showing you that this kind of overlaps on top of it. Okay? Let's do natural log of x. And we'll put all of this on our notes here in a minute. And if you want to the link to this is on my website, so you can go to the site and do this activity again on your own if you need just a little bit more time. Okay, so here's natural log of x. How are e to the x and natural log of x related? That's exactly right. They're inverses of each other. So remember how e to the x had a horizontal asymptote? What type of asymptote do I have now?
Vertical.
Vertical. Okay, so if I kind of just start off showing the tangent line, look at the slope. The slope is still positive, but not increasing anymore. What's happening?
Decreasing.
The slope is decreasing. The derivative is decreasing. That means also that this graph has concave down, which we can see that that's true. This is a concave down graph, whereas e to the x was concave up. All right, so let's see what this derivative looks like. Okay. Okay, so again, just so that you know how this works, it takes basically at a point, it evaluates using a logarithm or an algorithm what the slope of that point is, and then it plots that y value. Okay, so this is not the same, but this is a familiar parent function. It's really only part of it though. It's only the right half. And that's because you cannot take natural log of negative numbers. You can only take natural log of positive numbers. So that's why this parent function may not seem totally familiar because I'm only seeing part of it. Anybody know which parent function this is? If it helps, your
which parent function?
Yeah, like one of your other parent functions that you know, so not square root of x, but you're on the right track. 1 over x. So 1 over x graphs this red part up here. Now, it also graphs something,
X is that one.
yeah, it also graphs something over here. All right, but, so you may say, well, they're not really derivatives because the whole thing's not there. Well, they are derivatives. It's kind of like when we say x squared and square root of x are derivatives, but there's a domain issue. That's why that happens here. So again, I've very informally proved to you that the derivative of natural log of x is 1 over x. Okay. In the end, this is just something you're going to have to know. So let's go ahead and kind of go over this in our notes. So we did this one last. All right, so the derivative of the natural log function, derivative of natural log of x is 1 over x. In your little green cards that you got yesterday, this is one of those. It'll help you remember. However, we're not just going to take natural log of x. We're going to take natural log of lots of things. And if you kind of skip down here to example 1, we can take natural log of a polynomial. You can take natural log of a radical, of sine or cosine, any of that stuff. So we have to have a more in general rule. So in general, the derivative is 1 over u times, and then using chain rule, we got to take the derivative of the inside. And I could write it as u prime, but I'm actually going to write it as du. And this is good. This is a good way to kind of start out. What's going to be more helpful and more concise is to write this as du over u. In other words, anytime you're taking derivative of a natural log, you look at what your argument is. What are you taking natural log of? The derivative goes on top, the original goes on the bottom. And we're going to practice this here in just a little bit. But I wanted to get the rule out there, and what I want to do now is kind of review some log properties. Okay? So I want you to look at A through F. I'm going to give you like 30 seconds to see how much of this you remember, just like really well. So fill in any of that you know. Okay, time's up. That's okay if you don't remember all of it, but does anybody remember what natural log of e is? It is 1. That's because those things are inverses of each other. What about natural log of 1? It is 0.
Oh my God.
You need to know that. When we're simplifying and dealing with this, it's important to know that natural log of 1 is 0. What's natural log of a negative number?
It doesn't exist.
Does not exist. That's important too. Because it has to do with the fact that natural log is the same as log base e. So remember, log is just like a backwards way of writing an exponent. So you're saying e to what power equals that thing. So you can't take e to any power and get a negative number. E to any power is always positive. All right, what about natural log of a times b? That can be spread out into 2 logs.
Oh, LA plus LB.
That's right. You may be thinking, oh, times, but it's actually plus. And this has to do with a similar exponent rule. So the reason this is important is because we're about to take derivatives, and if I don't have to use product rule, I don't want to use product rule. Okay, taking 2 easy derivatives sounds a lot better to me than taking one really complicated derivative. All right, do you remember what happens with this power of n? It goes to the front as a coefficient. So n times natural log of a. And that's called the power rule, and that's also important because when we're taking derivatives, if we don't have to deal with an exponent, that's better because that may mean no chain rule. Okay? What about e? E is similar to c. Natural log of a minus natural log of b. And then putting this all together, what about f?
Isn't it just the coefficient like n?
Yeah, it's just n. So what's natural log of e to the fifth? 5. Okay, again, if you can simplify something down, it makes taking the derivative easier. All right, so let's apply these to do one expand problem, one condense, and then we'll get on with the calculus. So expanding, I have one single natural log, but I have 3 groups. Okay, I have 3 groups. So I'm actually going to have 3 natural log statements. Okay, let's just look at the top. What can happen with that 5? Goes to the front. So that becomes 5 natural log of x squared plus 3. All right, now the next 2 items are in the denominator. So I need to go minus natural log of x. And then I need to go minus again because this is in the denominator. I get that it's being multiplied to the x, but for the whole fraction, it's still being divided. I need to do 1/2, right, because of the square root. And maybe we need to write that here. Square root means the same thing as 1/2 power. So the 1/2 goes to the front. Natural log of x squared plus 1. So we haven't really done any deriving problems. But I just want you to see, if I'm supposed to do a lot of deriving, I don't want to take derivative of something where I have chain rule embedded in quotient rule, embedded in product rule, and another chain rule. I don't want to have to do that if I don't have to. Splitting this up makes this into 3 easy problems. We're not going to do the deriving just yet, but this is why we're doing this. Okay? Condensing. I want you to do this one on your own. Okay? You're going to condense it into a single logarithm. There is some minus signs there, so we're definitely going to have a fraction with the denominator. So go ahead and try to do this. This is just reverse of what we just did. Do this part on your own. If you're stuck, you may be thinking, okay, which variables are going to go on the top, which variables are going to go on the bottom, which one have exponents. When you get your answer, compare with someone else in your area. Or if you're stuck, cheat, look on theirs, see if it sparks a memory or gets you an idea in your head that you can finish out. How many of you started by looking at the coefficients and rewrote them as powers? Did any of you do this first? If not, and you were struggling, this might be a good idea for you to kind of rewrite them as powers. How do you know what goes in the numerator and what goes in the denominator? Magic? Yeah, the positives and the negatives. So k is a positive log, therefore k goes in the numerator. What else goes in the numerator? X cubed. Some of you might have written 3x in the numerator, but you didn't follow that property, property D, which has to do with powers. The last 2 logs were negative, so both of those terms should go in the denominator. I see students here wanting to say, no, it should be y squared divided by z to the 4th. That is a mistake, and it's just you're making it harder than it needs to be. It's a positive log, numerator, negative, denominator. That's really all you need to think about. Okay, so let's apply this. We're going to use some of these log properties more than others, so we're going to start here with number 1. Now, is there any property I can use to break this up, simplify it down, anything like that? Nope, I can't. Because of this plus, I don't have a property for that. So don't overuse the properties. If this had been x squared times 3, then I could break it up. All right, so I'm going to just go straight into the derivative. Now, I'm going to write over here, you have it at the top, but I'm going to go ahead and write du over u. The derivative of u over u. So where's the u in this problem? In the parentheses. This part right here, that's what u equals. So all you got to do is write your fraction bar and think, okay, what's the derivative of u? 2x. What's u? X squared plus 3. And that's your answer. So once you get the rule down, it's really not that bad.
Where does it say du over u on our sheet? Other than what?
Up in the box.
Okay.
Okay, look at problem 2. Can we use a property?
Yeah.
Which one?
I don't know what it's called, but we can move 3 to the front. X.
LNFD.
Oh wait, I'm
So
looking at the
we're-
wrong question.
Okay, so let me say this.
Y equals
Some of you are
LNF.
thinking, hey, move this x to the power. There's 2 reasons why we don't want to do that. One, x is not a number. It's a variable, so I can't do that. But here's the other thing. So let me write this over here. This
So
is,
that's just like,
do you know how to take derivative of that? Neither do I. So we don't want to do that. It's not a bad thought. It's a good thought to have, but we don't want to do that. So again, there's no properties. But this is x times natural log of x. When I put the parentheses there, hopefully that reminds you of some rule that we have about taking derivatives. Product rule. So we would have y prime equals 1 times natural log x plus x times 1 over x. What I'm doing here is just derivative of the first times the second, and then plus switch it up. The only other thing that I want to talk about with this problem is that if this was a multiple choice, okay, let me back up. If this was free response, this answer is perfect. You will get all of the points, and I will be very happy. But if this was a multiple choice question, the answer choices aren't going to look like this. They're going to be simplified. So we're going to work on that a little bit today. So what do you think the multiple choice answer will look like? Yeah, natural log x plus 1. They're not going to have the 1 times. Again, there's nothing wrong with it. But if you're trying to pick out the right answer from a list, you got to be able to simplify sometimes. All right, number 3. Is there a log property I can use that will make this problem easier? I see a power. Note the hesitation in my voice. I see a power, but...
it's
Okay, look at property D and look at example 3.
Say it louder. Chain type of parentheses.
I am going to use chain rule, but I'm still on why can I not use that property?
Because it's outside of the parentheses.
Outside of the parentheses, the whole thing is being cubed instead of just the x. So chain rule, M and M. Okay, 3 goes to the front. Leave natural log x alone. The power goes down by 1. That's the first part of chain rule. And then you go times the derivative of natural log of x, which we know today is 1 over x. Now, the multiple choice of this probably just puts this all over x. I'm not going to rewrite that because that would be easy to match up if you needed to. All right, now problem 4, we can use the log property, and you want to, if you can. Okay, so again, just like before, I'm going to change that radical symbol into parentheses and 1/2. So see how this is different than 3. Only the log argument is being taken to the power. That means that you can use the property that puts the 1/2 out front. You don't have to do this, guys, but I promise you it will make it easier, especially on a multiple choice where you're going to have to simplify your answer to figure out the right answer. So if you do this, then the derivative is just going to be 1/2, because that's just a number, so we get to just write it and say times. Okay, remember, taking derivative of natural log of something. You take the derivative of that, x plus 1, that's a 1, and then x plus 1 itself goes in the numerator. And this is totally acceptable for an answer, except probably on a multiple choice it would be written like this, where they kind of put this into one fraction. Now, if you didn't use the log property, like you never rewrote it right here, it would be a lot harder for you to get that simplified answer. You're going to have to do more work there. So using the log properties makes the problem easier, and it helps you get the right answer. It's not necessary, but it's easier. All right, so we're going to leave natural log x alone for a few minutes, and we're going to talk about e to the x. So this is the thing we did first on the computer. Remember we took, when we did derivative of e to the x, what happened? It was still just e to the x. So derivative of e to the u is going to be e to the u times, again, we're going to apply chain rule and write times du. What this allows us to do is to take derivative of e to any power we want. Okay, so it's the same times the derivative of the inside. It's an application of chain rule. Okay, this part right here, we already talked about when we were looking at the applet on the computer. So let's go ahead and look at the next page. All right, so number 5. Y'all are going to like these because they're super easy. Okay, when you see an e to a power and you got to take derivative, first thing is you are just going to rewrite it. Times. So rewrite it, write your times sign, and then think, okay, what was my u? The u in this case is the power. So what's the derivative of u? 3. And probably on a multiple choice, they would move that 3 to the front. You do not have to do that. Like when you're just giving me an answer, you don't have to simplify it. But I just want you to be prepared again, like I said, for multiple choice questions. Okay, so I want you to try 6 on your own. It's a little bit harder, but you can do it. It's the same idea as the one we just did. Okay, look up at the board. How many of you started the problem the way I started it? This is the easy part, by the way. Just rewrite it. Okay, guess what? That got you like half the points right there. Okay? Now, how are you going to get the other half? You got to take derivative of that negative 7 over x squared. How many of you did quotient rule? Okay, it's not wrong, but you're working too hard for your money. You do it that way. How many of you rewrote it? I'm not going to ask how many of you just waited for me to give you the answer. But if you rewrite it this way, and this is kind of how we started derivatives, you're rewriting things, making it easier. So what's the derivative of this? 14x to the negative 3. So that's what I'm going to multiply here. All right, and again, this is a beautiful answer, 100% of the credit. Nothing wrong with this. Great. But if it's a multiple choice, the answer choice will probably not look like this. Okay, so let's think about some ways that we could rewrite this. So first of all, that 14 is probably going to be moved to the front. And then what's going to happen with this x to the negative 3? Yeah, it goes divide by x cubed. So the blue answer is great, the green answer is great. You don't ever have to simplify, but you need to be comfortable enough with it that you can do it when you need to. Okay, you want to hear some good news?
Yes.
Yeah.
We're going to skip number 7.
No, that's bad news.
All right. So number 8, locate the relative extrema. Now don't get bogged down in that we're doing something new. Just think, before today, if I said find the relative extrema and you're given an equation, what's the first thing you do? Derivative. Derivative and set the derivative equal to 0. So let's find the derivative here. We are going to have to use product rule, right? So derivative of x is 1 times just e to the x plus just the x times the derivative of e to the x, which is e to the x. It's kind of weird, but remember, derivative of e to the x is just e to the x. If you say, well, I put a times 1 here, that's perfect. There's no problem with that. All right, now, when I set this equal to 0, you might be thinking, well, I don't know how to solve that. But you do. What did we do before? When we had a polynomial equal to 0, we factored. We're going to factor here. We're just going to factor out a GCF. That's going to be e to the x. And this is where it's really convenient that e to the x is its own derivative, because otherwise this would actually be really hard to figure out. So when I factor out e to the x, I'm left with 1 plus x in parentheses. And so then you get to set each thing equal to 0. And I'll do the easy one. How are you going to do the other one? So there's a couple different ways to think about this. Is it even possible? So I heard natural log. Could we take natural log of both sides? Yes. But what's natural log of 0? It doesn't exist. Remember, there was an asymptote there. Here's another thing to consider. E to the x is always positive. Always. It's never 0. It is never negative. Okay? Just like how I can only take natural log of positive numbers, e to the x is itself always a positive number. So if e to the x is always positive, it cannot be 0. All right, so I have one single critical number. Let's put it on a sign chart, and let's plug it into the derivative. Now, I'm going to circle this derivative. Now, do you remember what I just said about e to the x? It's always what?
It's always positive.
It's always positive. So put a big giant plus on top of e to the x. Because when we're trying to do a test, if you don't have to try to figure out, what is e squared? Don't worry about that. You don't have to know. Okay? So if I plug in a number like -2, I get negative. Therefore, f is decreasing on that interval. If I plug in a number over here, I get positive. And I'm going through that part fast because you guys know how to do this. This is old stuff. So we have a relative min occurring at x equals -1. If you wanted to find the y value of that min, what would you do?
Plug it into the original equation.
Plug -1 back into the original. We're not going to do that. You could also tell me where this graph is increasing, decreasing. We could take second derivative and do concavity. I mean, the possibilities are endless. But for today, we'll just move on. Okay, number 9. Number 9, implicit differentiation. This has been on almost every single after party. That's because I really want you guys to be good at it. It is all over my semester exam. You really need to be very comfortable with implicit differentiation. So, derivative of x squared, 2x. Derivative of -3 natural log y. Okay, so that's going to be -3. What's the derivative of natural log of y? This is new today. 1 over y. And since I'm deriving implicitly and I just took a derivative of y, I have to write dy over dx.
Why is it 1 over 5?
Because natural log of x, derivative of natural log of x is 1 over x.
So it's just substituting variables.
It's just the same idea. You technically could put the dy over dx on the top. That, the way I've written it here is better. All right, and then what would the last term be? 2y dy over dx equals what? 0. Okay, now your goal is to get dy over dx by itself. I want you to do this. You do this by yourself. Well, there's 2 steps here. Keep the dy over dx terms on the left, move the other terms to the right, factor to the right. Technically 3 steps, I guess. Okay, compare your answer with mine. And I'll put a little ... here because I did not show all the steps. All right, so let's move on to another problem. 10, equation of a tangent line. What do you need to write an equation of a line? You need 3 things. Okay. If we knew an intercept, that would be great, but we typically don't know. So we need a point. We need an x, which we know. We need a y, which sometimes we're given, sometimes we're not given, and we need a slope. Okay, so let's find the y first, because that's where we just plug 1 in to the original. So that would be 3 times 1 minus natural log of 1. What's natural log of 1 again? 0. So we get 3. That's my y value. Okay, sometimes that's given, sometimes you have to find it. You can do all of that before you even take the derivative. The derivative is what's going to help me find slope. So y prime, derivative of 3x squared, that's easy, that's just 6x. Now, to do the next part, I'm going to let you kind of do this on your own. Think of this. You could just go straight into doing the derivative of natural log, or you could use a property. So I want you to finish the derivative. And then I want you to find slope by plugging 1 into the derivative. So you're doing this little part on your own. You can use a log property, but you don't have to. You get the same answer either way. Okay, so if you did use the log property, you would have moved that 2 to the front, and so then the derivative would just be 2 times 1 over x. How many of you, instead of this, wrote x squared, or 2x over x squared? You're going to end up getting the same number. So for my m, it's going to be 6 times 1 minus 2 times 1 over 1. So what's that? 4. So you should get a slope of 4, no matter which way you did it. Then my answer, then final answer is going to be y minus 3 equals 4x minus 1, because that's just to write the equation of the line. This also is something you have had to do on your after parties a lot. That's because I really want you to be comfortable with it. Okay, last problem, number 11. For 1970 to 1990, number of medical doctors is modeled by this really weird exponential equation, where t equals 0 is 1970. At what rate, that word rate is my clue that I'm going to have to do a derivative, is the number of doctors changing in 1988. So first of all, what does t equal in 1988?
Years.
18. So let's pretend that someone just walked in and they're like, I know what to do. Let's just plug 18 into the equation right now. What would that find? Don't give me the number, just like in words.
The number of doctors.
The number of doctors, which is a great Algebra 2 level question. Even Algebra 1 maybe. But we want to know the rate at which the number of doctors is changing. So we need to find the derivative before we plug in 18. Okay, so let's do this one together because it's kind of been a long lesson. So we rewrite it first, right? That's what we do with e to the x. Then we got to go times the derivative of the power. So times the du. Okay, and in this problem, the u part is that whole power. So what's the derivative of that power? Exactly. So don't forget that. Don't forget that. All right, and then to finish this problem out, you just need to take 18 and plug it in for t. I'm going to let you do this part on your own, and I'll give the answer tomorrow. And then your homework is to do 1 through 13, so just that next page. Okay?